Hello friends, welcome to the channel Physics by IITians. So we are continuing our laser lecture. Last time we have seen that what are the types of active medium, the 2 energy level system, laser system, 3 level laser system, 4 level laser system we have discussed. Today we will discuss the threshold condition for the oscillation, and also we discuss the modes of laser beam. Okay, so let's start. The threshold condition for oscillation, what do you mean by threshold? Threshold value is at that value when the oscillation will happen. So what do you mean by oscillation? Because we have already told that for laser we need three things. One is the active medium, another is the population inversion. So we need some pumping scheme. So this is pumping, and the third one is the resonator. Okay, resonator. So resonator is playing the role for the oscillation. Okay, so in last video I also discussed it thoroughly, and also we are looking here how this is doing lasing action. So you have this active medium and you have two resonators. Suppose this is the two plane mirrors. Okay, this is the two plane parallel mirrors, and you have an active medium within these two parallel plane mirrors, and you are doing pumping. Okay, so for to get achieve population inversion. So whenever there is pumping, so the atoms from the ground state, it will go excited, it will go to the excited state, and it will obviously it will spontaneously emit to the ground state. Now the spontaneously emitted photon will, suppose this is the spontaneously emitted photon, it can also become a stimuli for the other atoms to come to the ground state, because of the population inversion scheme we have already n2 is greater than n1. So for a one photon, that can will act as a source or stimuli for the stimulated emission. So for one spontaneous photon we can get two photons. Okay, so from now it will go certain, it will distance travel some distance from this mirror up to this mirror, and it will come back. So after coming back to this through this active medium, it will also excite some other photons, some other atoms to stimulate for the stimulated emission of radiation. So for each and every round trip there will be number of photons that are increasing. Okay, so this is the basic physics, that one single photon can become a stimuli for the stimulated emission. Okay, so for one round trip the photons can excite much more atoms for the stimulated emission. From another round trip the photon can excite another set of atoms, and it can come back to the ground state and producing stimulated emission. So the stimulated emission is the main process for the lasing action, because from one photon your photon is becoming amplified. The number of photons you are getting, that is much greater. So this, the resonator is giving you as a positive feedback to your laser system or to the active medium to producing laser, for producing laser. Now you have some question, may have the question that what are the conditions for the laser. I mean, these are all the ideal case that I thought that mirror is 100% reflective, this mirror is also 100% reflective. Okay, if we need some certain laser, so this mirror should be 98% reflective, because we need some output. So 2% output is going and we getting it as an output, that is laser output. Now we all know that none in the universe is 100%, can be, none of the material can be 100% reflective. So it may be certain 95% or 96% reflective, or it may be certain 97.5% reflective. Suppose I am telling you. So there should be some losses. Also due to the spontaneous emission also, there should be also the scattering of the photons. It is not like that only the photons are unidirectional, this is going like this way. So photons are emitting everywhere in every direction from the active medium. So we are basically collecting a unidirectional photon, the photon which are along the axis of the active medium. So our laser should be unidirectional or coherent beam. So coherent I will come later time. This is the unidirectional beam. So the photons only in the on axis photons can amplify, and other photons will get out from this active medium or the resonator system. So the losses due to the scattering, the losses due to the diffraction inside the active medium, the losses due to the mirror reflections, because there are certain kind of transmission from both the mirrors, because none of the mirror is 100% reflective, so there should be some loss. Now the laser will only happen when the gain at the medium will be greater than the loss within the medium. So whenever the gain will be greater than the loss, then we can get only the laser, which is laser output. Now when this is threshold frequency, means the threshold condition means when gain is exactly equal to the loss. So this is the threshold, means this is the trigger condition that can give us the lasing action. So let us try to calculate the threshold condition for the oscillation. Okay. So what I have drawn it separately. That you have two mirrors, M1, M2, and you have the reflectivity of M1 is R1 and M2 is R2, and the distance between M1 and M2 is L, and in between them there is active medium. Now the light is traveling round trip path, because it is going to this mirror, coming back, then reflecting this mirror, coming back, reflecting this mirror. It is doing a round trip path. Okay. So in traveling from mirror M1 to M2, the light intensity increases from I0 to I of N. Suppose though initially the light has intensity I0, so it will get amplified due to this due to the oscillator, and the increase it from I0 to IL. So IL will be increasing factor. Suppose if there is no loss, then the IL should be I0 into e to the power gamma into L, where gamma is the gain at the medium, gain of the light at this active medium. Now this gamma factor will be modified, and it will become gamma minus alpha s into L due to this losses inside the active medium or inside the system. So the light signal or intensity of the light signal should be I0 into to the power gamma minus alpha s into L, which is going from this traveling a L distance, that from M1 to M2. Light is going from M1 to M2. The intensity of the light get amplified like this form. Okay, where we have also associated the gain term as well as the loss term. Now alpha is the losses. I have told you, mainly due to the transmission through the mirrors, mainly due to the scattering, due to the diffraction within the medium. Now after a complete round trip, earlier this was calculated only for one single path, that is M1 to M2 or M2 to M1. So whenever we complete round trip, we will consider the distance as 2L. So the intensity after complete round trip will be, suppose from here to here it can go, and then it will reflect back. So this component will be modified with the reflection coefficient R1, and after here also it will reflect back. So this total component or complete round trip I2L will be amplified, will be modified with the two terms, the reflection coefficient of R1 into R2 into I0 e to the power gamma minus alpha s into 2L, because you have to understand that for the one round trip the light is going up to travel up to distance L, so we get this intensity, this much amount of intensity. So whenever it reflect at mirror M2, the intensity will be R1 into I0 into e to the power gamma minus alpha s into the distance, and whenever it, then again it will come back and reflect the mirror. So that component will be R1 into R2 into I0 e to the power gamma minus alpha s into 12. Okay. So whatever I write this exactly, this after the complete round trip where the light has traveled a distance 12, the amplification of the light intensity will be R1 R2 I0 to the power gamma minus alpha s into twice L. Now the amplification factor, we all know that amplification should be the amplified signal divided by the initial signal. So I12 divided by I0, so which will be surely then I0 will be cancelled out. So R1 into R2 into to the power gamma minus alpha s into 12. Now threshold condition will happen. Means the minimum condition for the lasing is that G is equal to 1, that is the gain equals to loss. So that will be that up now if you want laser, so threshold is G into 1, so your G equals to 1, so your condition for gain should be greater than 1 for the laser. So this factor, that is 2 into L into gamma minus alpha s, that is this factor, because these are two constant R1 R2, the reflection coefficients of the mirror, you cannot do anything with those. You want to do what you can achieve, that you want to achieve the maximum reflectivity of the two mirrors, but you are unable to make it 100% reflective. So what we can do, we can adjust the length of the oscillator, we can adjust the losses somehow, that it should be, losses should be minimum and gain should be maximum. So we are not taking this term, but whatever in our control, we are taking that term, that is this e to the power 2 into gamma minus alpha s into L is greater than or equals to 1 by R1 R2. So gamma should be greater than or equals to alpha s, that is this loss term, plus 1 by twice L into Ln 1 by R1 R2. So this is the gain factor, which should be at least greater than this quantity, that is alpha s, this is losses due to the scattering mainly, that's why I denote it as alpha s, plus 1 by twice L Ln 1 by R2. So what you can achieve, that you can make it in your way, that is 2L, it is in your hand, that is the length of the oscillator or length of the system, okay, because you want to make it maximum R1 R2, you make it maximum reflective, that is maximum 100%. Now this is the condition for the lasing. Now whatever we have understood, that the laser, if we achieve threshold value and if we somehow make the gain is greater than the loss, then we can have an amplified output in the form of laser. Now we will study that the mode of laser beam. Suppose the laser, you have some question that the laser output, the light output we are getting, is it random? Because it is not random. We always know that in case of laser, they are coherent, they are monochromatic, they are unidirectional, so they cannot be random. So if they are random, then there should be no difference between any ordinary light and laser. So since there is a huge difference between an ordinary light and laser, so laser modes have some definite, there are some definite laser modes. And what does it mean? So this is the active medium, this is the laser system. So this is, if the length is L, now those light signals or those modes will be amplified when this condition, that is if the N is the refractive index inside the medium and 2 into L, this is the round trip path traveled by the light, is m into lambda. What does it mean? This means that the constructive interference condition, those modes which are satisfying the condition for the constructive interference, only those modes can amplify. Otherwise, those modes which are destructively interfere with each other, they will attenuate it and they will not get any contribution for laser. Now, these modes are called longitudinal modes, because these modes we are taking, this is along the length of the laser cavity, okay. So these modes are called the longitudinal modes and m is the mode number. So we can have a look on the definition, that the laser modes governed by the axial dimension of the resonant cavity is longitudinal mode. So 2 into n into n equals to m into lambda. Why we are taking 2n? Because we have to consider the round trip oscillation or round trip path traveled by the photons. Okay. So this is 2n equals to m lambda. That is the constructive interference condition for the photons. So you have to understand that those photons which will constructively interfere, only they can take part for the laser. Now mu m, if we lambda, replace the lambda, so if we want this in terms of frequency, we can get mu m equals to c by n into lambda m, or equals to m into c by twice n L. So what are the numbers? I mean, how many modes, longitudinal modes are possible? Suppose you have take a laser cavity, that is L equals to 0.5 meter and lambda equals to 5000 angstrom. You have number of modes, huge number of longitudinal modes, that is 2 into 10 to the power 6. That number of longitudinal modes are possible. And what are the separation between the longitudinal? What are the separation between the two modes? This is C by twice n L. So if I plot how the spectrum, how do the spectrum will look like? The spectrum will look like, these are the modes. Suppose this is nu m, this is nu m plus 1, this is nu m minus 1, and the difference, the separation between them should be C by twice n L. Okay, these are the modes, longitudinal modes which I am getting. Now we all know that this nu m has a natural width. It is not a single, it cannot be a single line, because some natural line width, due to some broadening, collision broadening, Doppler broadening effect, one single frequency we cannot achieve. If we somehow eliminate all the effects, but due to its natural line width, that is del E into del T should be greater than equals to h cross by 2, the one frequency will not be one frequency, it will have some natural bandwidth which will be Lorentzian curve, and this with is delta nu and the frequency at nu. Okay, so you will get like this. Now what will be the, this is the frequency separation. What will be the wavelength separation between the two lambdas? That is lambda square by twice n L. Now this is the longitudinal mode. Now whenever, which kind of modes only can contribute to the laser? Those modes which have gain is greater than loss, those modes can only develop and contribute to the laser. Okay, so if suppose this is the gain, okay, this is the loss profile, and you have this mode, so only those modes which can become the gain of those modes which can greater than the loss line, those modes can develop inside the laser medium, and it can contribute to the laser frequencies or laser output. Now this is the longitudinal direction, we are taking longitudinal modes. This is along the axis or axial direction. Now if you take your laser and you want to find out what are the transverse distribution, how the laser photons are distributed perpendicular to axis. So you take the laser beam, you somehow put a concave lens, and then it will diverge, and you take a photographic plate. So you will see that the mode distribution of modes can be like this, the uniform distribution. It can be like a this shape also. It can become this shape also. It can become this shape also. So what does it mean? So this kind of distribution, that is, I am showing it here. I think you all can see this. This is visible, I think. So this kind of distribution, the mode distribution, these are called the transverse mode of lasers. And this is transverse mode, and this is TEM00 mode, that is the Gaussian mode. Now what does it mean? This is a Gaussian like distribution. The intensity will be maximum at, suppose this is here, the intensity is maximum, that is I0, and it will exponentially decay to the other sides. Okay, now you are seeing that this is the distribution of the transverse mode. And how do you find that? You have to first, suppose these are the two directions, one along, suppose this is along P and this is along Q. So you have to name it like TEM mode PQ. Okay, now what is the TM00 mode means? There is no node. If you go along this direction, along P direction or along Q direction, you won't get any intensity change. That is, you don't get any node. Node means the zero intensity. You don't get any node. So it will be 0, 0. Whenever you, after going through any axis, going along any axis, if you get any node that is change in intensity, you will take it as 1. Suppose that I am going along this direction, okay, along Q direction. This TEM for Q, I don't get any change in the direction. There is no node along this Q direction. This should be 0. But if you go along P direction, there is the change and there is a node. So it should be TEM10 node. Now if you go along this direction, this is along this direction we are finding that there is a node. So the Q, this is along Q, so there will be 1. And if you are going along P direction, there is no node, so this should be TEM01. Similarly, if we go along the Q direction, that is along this direction, there is also node, so it is also 1. And if you are also going along P direction, you are also getting another node. So TEM11 node. So these are the way of defining the transverse modes. So the nodes and we are getting, then we will denote it by 1. And if we don't get any intensity change, any node, so that will be 0. Another important thing that I forgot to mention, that the longitudinal modes, whenever we are talking about that, there are mirrors, and this is the formula. Only those modes will develop that are satisfying the interference, that is constructive interference condition, and it is generating a standing wave, okay, because if you have to consider it like a string that is plucked, okay, so you will get standing waves. So this condition is the condition for the standing wave generation. So you will certainly develop standing waves inside the resonator. Okay, this is the, so resonator can be, the oscillation can be like this, or oscillation can be like this, or oscillation can be like this. What you have to certainly remember, sorry for extra overpopulated oscillations, so I make it clear, draw that this can be like this, but what you have to think, that there should be nodes at the mirrors or at the boundaries. This is the formation of standing waves. So this is the whole physics between the transverse wave behind the longitudinal waves, the modes of laser beam, the threshold condition for the laser. Hopefully you can understand today's lecture. Next day I will discuss about the coherence. What do you mean by longitudinal coherence? What do you mean by temporal coherence? So hopefully you understand this video. If you like our channel, please subscribe the channel, share with your friends. Also like our Telegram page. Thank you.